Click the
Hey
link
guys,
in the
Russ here. Welcome
description
back
to
to my organic
download your
chemistry
own
videos,
copy
and
of this
today
video's
we're
problem.
going to talk more about pKa's, acids and bases, and all that fun stuff. Let's get after it. Explain the differences between the pKa of the following acids. They're both carboxylic acids. Okay, let's talk about it. Well, whenever I have an acid-base question, I always do the same thing. And I tell my students to do the same thing, and they never do it. And they get it wrong. Always react it with water. Because pKa's are almost always done in water. So you're going to get hydronium. You always are going to make hydronium. Now remember, if you have an anion, just go ahead and resonate it right away. Just in case. The resonance may not tell you anything, but let's be honest, it's probably going to be the correct answer, right? One resonates, one doesn't. That's usually how these things go. One anion resonates and puts the oxygens to have the negative charge, one doesn't. There we go. So there's the resonance form for that particular anion. Let's go to the bottom one. Let's make that one purple. And it resonates, so just do that right away. I'm sure we'll find the answer in the resonance forms. I mean, Dr. Betts did say if you don't know the answer, just say resonance. So one of them has, wait a minute now. They both have resonance forms. Oh, okay. Well, one must be better than the other. Well, they both put the negative charge on oxygen twice. They both have two resonance forms. They look basically equivalent. That's not good. Well, what if it's not resonance, what else could it be? Ha! Resonance doesn't always tell you the whole story. In fact, a lot of times it doesn't tell you much about the story. A lot of times it does though too, so never ever discount resonance. Well, the bottom one has that chlorine right there. Okay, well, chlorine is electronegative. So that means that the chlorine is going to be attracting electron density to itself. So we could draw these types of little chevrons here, which basically means that the electron density is being pulled through the sigma bond towards the chlorine. Okay, that makes sense. Okay, well, remember, that's called induction, right? When you pull electron density through sigma bonds, that's called induction. Well, then that must mean there's another chevron there, because remember, induction only occurs over 3 bonds. So that means the biggest pull is on this carbon, but this carbon is also pulling on that bond. So this carbon right there is delta positive. Okay, that makes sense. Because the chlorine is making that carbon more delta positive than normal. Does that tell us anything, though? It does, actually. It tells us a lot. That carbon is more delta positive than a normal acetate carbon. So this carbon here is delta positive too, no doubt, but not as delta positive as this one. This one has a huge delta positive, okay, in comparison to this one. Now let's think about that in terms of acids and bases. If you're basic, you want to react with a proton. You're attracted to a proton. Okay, makes sense. Well, things that are attracted to protons, because protons are positive, are negative. Now remember, atoms aren't thinking or considering or choosing. They're responding to the energies that are around them. Okay? Well, if this carbon is more positive, more delta positive, than this one, that means the electrons that are here are being attracted this way. They're being attracted towards that carbon. Well, so are these ones, right? But these ones are attracted more because of the larger delta positive. So the negative has a choice, right? it wants to be attracted to positive charges. Well, this positive charge is right there, and it's attached to me. So I'm going to be attracted to this. So my electron density here is being pulled into this. This oxygen is losing some electron density this way because of the inductive effect of this chlorine pulling electrons towards itself, making this carbon more delta positive than normal. This would be normal. These electrons are being pulled towards the central carbon, if you will, making those oxygens less negative, making them less attractive to a proton, making them collide less with protons, making them collide slower with protons, and in turn, making the base more stable or less reactive, okay, less prone to collide. It's called the inductive effect. And induction is another way anions can become stabilized. Resonance is the best. Resonance overweighs everything. But inductive effect cannot be discounted, especially when you have the same resonance forms. You have the same number of resonance forms, the same number of resonance forms with the anion on oxygen. Okay, so here's an example of the inductive effect stabilizing a base because this carbon starts to pull electron density towards itself, making these oxygens less negative, less attractive to a plus charge. All right, again, guys, it's a very long explanation because it's very abstract, but it's something that you can consider. Let your mind marinate on it, let your mind wrap around it a little bit, and it's really not that difficult to contemplate. Now, with that, I really hope you liked this video. If you did, slap that like button, leave a comment below. Let me know how I can help you out in your organic chemistry endeavors. And you know what, guys, if you would please slap that subscribe button, become a member of the Dr. Best team so we can all do well in organic chemistry together. It's really something that it's not all that hard to do. We can do it together.
Email drbets@protonmail.com if you would like a copy of every problem in this series.
And good chemistry. We'll see you soon.